Hey everyone, welcome to this lecture on Introduction to Three-Dimensional Geometry. This is the third part of our series on coordinate geometry. In the first part, we talked about coordinate geometry in general. In the second part, we talked about conic sections. And this is the third part in which we'll be looking at three-dimensional geometry. This is basically an introduction to three-dimensional geometry. We'll be touching the parts on the definition of three-dimensional geometry, some of the continuation from two-dimensional geometry to three-dimensional geometry, and some of the formulas that are related to three-dimensional geometry. This section will be covered in two lectures. Basically, both the lectures will be sort of an introduction to three-dimensional geometry so that you get a really good feel of it and you understand the concepts well. So three-dimensional geometry, as the name tells you, is actually about a geometry dealing with three dimensions. It's just that it is this is what three-dimensional is. So thus far we've been talking about coordinate geometry in the x and the y planes. Every point has two coordinates, the x coordinate and the y coordinates. The first point representing the x-axis, like 2, 3 would be the point on the x-axis, and 3 would be the point with regards to a y-axis. Now we add a third dimension to it. So we can say that the previous geometry has been two-dimensional geometry dealing with one dimension, that is x, and the other dimension of space, that is y. So now we will be talking about the third dimension of geometry, and that is z. So this z over here represents the third dimension of the geometry in 3D geometry. So right now you don't have, this isn't how the graph, or this is how the planes of three-dimensional looks like. This is just one of the ways how it looks like. We're going to of course explain this again and in different ways. Right now it is one of the ways in which you can see three dimensions. This z is shown over here pointing towards the top, just so that you can get the grasp of the idea. You can visualize this, how the plane in three-dimensional geometry is. So another way to look at it is this. So if you look over here, this shows the axis of the three-dimensional geometry. So this, you have the y-axis over here, and this is the y-axis over there, and then you have a z-axis going across them. So just like in the two-dimensional geometry, we had a positive x-axis and negative x-axis, positive y-axis and negative y-axis. Over here in the z-axis we have the same thing. We have a positive z-axis and we have a negative z-axis. So like I told you before, don't think that this is what a three-dimensional plane looks like. This is just one of the visualizations to show you how the three axes in a three-dimensional space are organized with each other, with respect to each other. Every axis is perpendicular to each other. Y is perpendicular to z and x. X is perpendicular to y and z. Z is perpendicular to y and x, as you can see from the diagram over here. So moving on, just like we talked about in the two-dimensional geometry, the points over here, the three planes determined by the planes with axis are coordinate planes, and these are called x, y, y, z and zx. So what are we talking about over here? If you look over here, so we have three respective planes with regards to the axes. We have the xz plane, which will be this plane over here, which has no part of y in it. We have the x and the y part, that is this part over here, because it has the x and the y part in it, the axis in it, so this plane will be over here. Then we have the z and the y axis, which is this part over here, which is the plane. If you stretch it over here, I'll show you the visualization of the planes later on. But this point is basically to explain to you how the three planes are formed in a three-dimensional geometry graph. So now let's visualize these planes further so that you can have a better understanding of this. So now over here, I think you will be understanding it in a better way. So if you look over here, so let's take it step by step. This is the z plane, this is the x plane, and this is the y plane. The green is the y, red is the x, and the blue is the z plane. So this is to explain to you what these planes are if you want to visualize them. As you can see, all of these planes are perpendicular to the other two planes. One thing to remember over here that I want to explain to you through this slide is that these three coordinate planes, they divide the whole space, all of these x, y and z, the positive x, the positive y, the positive z, and the negatives of these, they all divide this into 8 parts. Each of these parts is called an octant. Now why is this called an octant? Because, you know, for oct is for 8, And if you want to see what these 8 parts are, if you look, this is one part over here, the other part is over here with these axes over here, and the third part is over here on this side, fourth is over here, fifth is over here, sixth is over here, and the seventh one is this, which is behind, we can't see that, and the eighth one is below that. So if these 3 planes over here, the x, y and z plane, and we'll be dividing this whole space into 8 octants. If you look over here, we have the origin. The origin will be the origin. It's not going to change this is still the origin, but the only difference is now it's going to have 3 coordinates. Rather than the origin being at 0, 0, it's now going to be at 0, 0, 0, because now we have to cater for the z coordinates, z-axis coordinates as well. So there will be every point in this space will be represented by 3 points. Now those 3 points will be, of course, the x, y and the z coordinate of the point. They could increase and decrease. Of course, by decrease over here I mean they could be 0, but they will be there because we are talking about the 3-dimensional geometry over here. So this is basically this is what it explains what I just said. So the coordinates of the origin are still going to be the same. It's 0. Instead of 0, 0 like it was in 2-dimensional geometry, it's going to be 0, 0, 0. Because we have to cater for the z-axis. Moving on, the coordinates of any point on the x-axis are of the type x, 0, 0. Now this is something that's, I think, really easy to understand, because we have been talking about in the 2-dimensional geometry, we talked about how anything on the y-axis is going to have a 0 x-axis value. Just like that, anything on the x-plane is going to have a 0 z and y value. If anything is on the x-plane right now, don't worry about anything being in space right now. I'm just trying to make clear the concept right now. Anything on the x-plane is actually going to be 0 with respect to z and y, just like it was in the coordinates, and the same goes for all the other planes as well. Anything on the y-axis are of the type, sorry, I was talking about the axis over there, not the planes, because the plane will have any point in space over here that's going to have 3 value. Any point that's over here is going to have a negative x, a positive z and a positive y value. But if anything is on the z-axis or anything is on the x-axis, it's going to have a value of x that could be any number. If it's a positive, it could be 3, 2 or 3. If it's on the negative side, it could be negative 2, negative 3. But other than that, it's going to have a 0 for the y and the z-axis, just like we talked about, just like it was in the 2-dimensional geometry. Now moving on, so in the z-axis, the same goes for the z-axis, the new axis that we introduced over here. So anything on the z-axis, like in the positive z-axis, is going to have a positive z value, but it's going to have zeros for the y and the zeros for the x. Just like that, if we move on from there, we now talk about the x coordinate of the point in the yz plane must be 0. Now you see, if anything is over here in right there in the open, of course it's going to have a 0. It's going to have 3 coordinates. On the other hand, if anything is exclusively in the yz plane, of course if anything is exclusively in the yz plane, it's not going to have an x-axis. So this is the one thing that's continuation of the concept that we just studied a second ago. That is, anything on one axis is not going to have, anything that lies on the axis is not going to have any other values for the coordinates. Just like that, anything that's going to be on the plane on a particular y or z or x or z or y and x, that's not going to have the value of a coordinate of the third axis. The x coordinate, what I mean by that is that x coordinate of the point in the yz plane must be 0. A point in the xy plane will have the z coordinate to be 0. A point in the xz plane will have the y coordinates to be 0. I mean, this is pretty straightforward if you look at it. It's just basically continuing what we talked about before. If you see now over here, you can see the definition of co-linear points. 3 points are said to be collinear if the sum of the distances between any 2 pair of points is equal to the distance between the third pair of points. So you take the point, the distance of one pair of points and add it to the distance of the second pair of points, and you match that with the distance of the third pair of points. You would have, if they are equal, you would call these points to be collinear. Of course, this has I was just introducing this so that you can understand the concept behind this term. You might be using this, of course, further on in your math and engineering. Now moving on, the distance formula over here, the distances. We've already talked about the planes. So if you look at this diagram over here, if you look at this xy plane over here, this is the xy plane. So any distance from any point, the distance from any point to this xy plane, the distance, I'm only talking about the distance right now, is of course going to be the distance is going to be the z coordinate. I mean, if you have a plane over here, xy, if this is a plane over here as drawn by my pointer over here, my cursor over here, so the distance from any point over here to this plane is going to be the z-axis. Just like that, if there's a plane of yz over here, the distance from this point to this point is going to be the x-axis, the value of x value, because the distance is perpendicular over here to the plane. The point is perpendicular. The distance of the point to the plane is perpendicular. So that's why we are going to have this as an indicator to the distance to that plane. So this is, this is pretty straightforward. If you have a point on a plane, if you have a point and you have a plane, the distance between this is going to be the direction of the axis from the point in the direction of the point that you're measuring the distance. So if you have these octants, I mean, of course you can, this is just to explain to you, if there's a point in the xyz octant, so that's just going to have a positive value for x, y and z coordinates. I mean, this is the xyz coordinate, this is x, y and z. So if you have anything over here in this region, if you have any point over here, is going to have three values. One is going to be the x and the y and the z. So all these values are basically going to be positive. So this basically graph basically shows that if in a particular coordinate, in a particular octant, you have a point, what will be the coordinate values of this point? What will be the sign of the coordinate values of the point? The positives or the negatives, or this positive and the negatives in any particular order. If you don't have to memorize this, you just have to visualize this. If you have anything over here, let's just say you have anything over here, this is the point right there. Now this of course is going to have a positive x value, a positive y value and a negative z value. So this graph basically shows this, nothing else. So you don't have to really memorize this. I was just pointing it out so that you know what we're talking about over here. Now this slide basically shows some of the formulas. Some of the formulas are pretty basic, just a continuation and the extension of the formulas that we have been studying before. Distance between 2 points was x square minus x1, x2 minus x1 whole square plus y2 minus y1 whole square and under root of all of this. So now we have a third point in this, so we're just going to have this. We're just going to add the third point into this, x2 minus z2 minus z1 whole square, and you're going to have the formula for the distance of between 2 points P and Q, which have x3 xyz and xyz for Q as well. So this we studied in the two-dimensional geometry. We had two formulas over there, we had two coordinates over there, x and y's, so we made a formula out of that. Over here we have 3, so we have a formula out of that. Now what if you have one point P and you want to find the distance with respect to Q? So Q over here, what if that is the origin? So if you want to find the distance from a point to the origin, you're going to have, this is the way to find that. It's basically an extension of the Pythagoras theorem, the hypotenuse that we studied over there. It was x and y, and we drew a line to that point from the origin, and we calculated it using a hypotenuse because it became a triangle. Over here it's pretty much the same thing, but let's not get into that. I don't want to confuse anyone. So this is how you do it. Now moving on, so if you want to find out the midpoint, so this formula over here gives the midpoint. Is same one as before. In two-dimensional geometry we studied about the midpoint, that was the 1 point plus the second point divided by 2, and y1 plus y2, the other dimensional point, and adding them and dividing them by 2 would give you the midpoint. And so this, in this particular case, we're just going to expand that to introduce z into it, and once you introduce z into it, we get the new midpoint formula. And moving on, we talk about one other thing, that is the coordinates of the centroid of the triangle. Of course, like you can memorize this formula, you can understand this, but I don't think you would be but let's just talk about this. If you have a triangle and you want to find the centroid of the triangles, the coordinates are basically found through this. It's pretty straightforward. You have 3 values of x, 3 values of y, and 3 values of z, and you divide them by 3. So it's pretty much like the midpoint formula. Only difference is that this is a triangle and there are 3 parts to it, so that's why we're dividing it by 3. So this is pretty much it for the introduction to the 3-dimensional geometry. We would be, once in the next lecture, we would be doing the same thing again from a different perspective. I will be introducing the 3-dimensional geometry to you again with the one additional formula, so that you people understand this, if just in case the concepts are hard to grasp. The main thing to remember in 3-dimensional geometry is that you should try to visualize this, because you can't draw 3-dimensional objects on a piece of paper. Of course, you can, in your best effort, you're going to miss out one or two planes, which won't give you the exact idea of the 3-dimensional geometry. But of course, you have it over here. We'll be discussing this in the next lecture, almost the same lecture, in the next video, with some new things and one other formula. Thank you very much for watching.